All right, welcome back to Lecture 5 of the networking class. We're going to be talking about reliable transport, which I think is pretty exciting. I think this lecture is going to get into some real interesting solutions to important problems on the internet, I think, for the first time maybe in this class. So last time we talked about DNS, which was a very important service that connects users to the machines they want to connect to. You can think of it as the internet's directory service for mapping from domain names to IP addresses. It's distributed and hierarchical to achieve good performance and to allow it to be administered by different entities around the world. There are 12 root level servers that are run by the ICANN, the Internet Corporation for Assigned Numbers and Names. And there are top level domain servers just below that level that manage .com, .org, .edu, and so forth. Okay, and then from there it just gets there are as many levels as there need to be to create domains as long with as many periods as you want to have. Okay, every subdomain, no matter what level it is in the domain hierarchy, has a set of authoritative name servers, which is where the IP address records, I guess you could say the DNS records, are stored and updated, and where everyone in the world will check to find what are the IP addresses for that domain. Although there is caching to prevent that server from having to handle too much load. There's caching throughout the system, both on the clients and in the resolvers and the near the clients. The basic records are called A records or quad A records that map from domain name to an IP address. There also are other types of records to handle other things like email. And there are registrars that sell domain names, and they're managed by each top-level domain separately. And finally, we showed how dynamic DNS servers that don't just have a single mapping from name to IP address, but have different mappings depending on who you are and when you ask. Those kinds of dynamic DNS servers can provide interesting services like load balancing, where you have lots of users accessing, let's say, google.com or facebook.com, but they all get sent to different IP addresses so that the load is handled by many machines. Even more clever than that are content delivery networks that look at where the request is coming from and kind of geolocate it to figure out where in the world that is and give you a answer IP address that is close to your location so that you'll get good performance when you visit the website or whatever service it is. Okay, so moving on, like I said, throughout the class, the internet has many layers of protocols to solve the various different problems that networking globally provides or confronts us with. Last time we talked about HTTP. We talked about DNS, but before that we talked about HTTP, which is an application layer protocol, which is like the lowest level or highest level, depending on how you're looking at it. If you're looking at the packet itself, it's at the end of the packet, which is what I've shown here. But you often will see diagrams where these things are stacked on top of each other, so it's the highest level. Okay, that's where you have the data that the programs are trying to communicate. Right above that, with HTTP, is the TCP protocol. And that's what we're going to begin to talk about today. What we're going to talk about today is not exactly TCP, but it's like a simplified version of TCP that solves many of the most important problems that TCP solves, which is reliable transport. Okay. So what this TCP layer, which in general is called the transport layer, provides is allowing multiple connections called sockets to be used by apps on a single machine. It does that by providing port numbers. We can call that multiplexing, more than one connection per machine. It also has to deal with the fact that internet packets have limited size, so the IP packets cannot have arbitrary size. So what TCP does is, even though your applications may want to send large messages, like download big web pages, TCP breaks those big messages into smaller messages that fit within the internet, in IP packets. So once you break a message into little pieces, it gets a lot more complicated because you have to reassemble them in the correct order. In addition, we said that internet packets are not guaranteed to be delivered. That's one of the things that makes the design of the internet of the core of the internet easier in some sense. The fact that a router can drop a packet anytime it wants to greatly simplifies the design of the internet. But in order to deal with that at the transport layer, we introduce acknowledgments of messaging. So when a TCP packet or segment, as they're called, is delivered, there should be some message sent back to the sender that tells the sender it was received. If not, then it needs to be retransmitted. There also is pacing introduced to this layer. So these are all things we're going to be talking about today, except for pacing will come later. Before we get to TCP, I'm going to spend just a couple minutes on what's called UDP, the User Datagram Protocol, because this is a simpler alternative to TCP that basically allows applications to use a type of messaging that is pretty similar to the basic IP messaging that the internet provides. Okay, we haven't defined IP really yet, but what UDP provides, User Datagram Protocol, provides the ability for applications to send datagrams or packets that one at a time that have to fit within a single actual packet that's sent. So I said before that messages on the internet, packets on the internet have limited size. If you're writing an application that's okay with that limitation, that the packets can't be larger than, let's say, typically 1,500 bytes, then UDP might work fine for you because it gives you direct access to sending those packets without somehow trying to hide that limitation on the size of the packets. UDP also accepts the fact that your packets could be lost, so it doesn't provide guarantees that your message will be delivered. If your application is okay with packets being dropped, then you might want to use the UDP protocol, use UDP sockets. So basically, the only thing that UDP provides to applications that is different than what IP provides below is port numbers and checksums. Port numbers, as we said before, are a way to have many different services and network connections operating on a single machine that has one IP address. And checksums, I'll show in a couple slides, are used to verify that the packet data wasn't corrupted while it was transmitted. Okay, so I think this will become a little bit more clear when I show what this UDP protocol actually gives in its headers. Okay, so UDP is a way of doing network communication that applications have access to. The application wants to send some data that's shown in the bottom as the application payload that's down here. So you want to send this data to another machine on the internet. You know its IP address. You also know the destination port number, and you provide a source port number. These port numbers are going to distinguish between the many different other connections that might exist on your machine and on the receiver's machine. Okay. So at the beginning of the message, we add a 16-bit port number field. This is a 16-bit integer, and 16-bit destination port number field. Another integer. We know with 16 bits, 2 to the 16 is 64,000. There are 64,000 different UDP ports available. There also, after that, you have a 16-bit integer that specifies the length of the application data. So if you're reading this packet, once you get here, you will know how much more to read down here. And finally, there's a checksum, which is some redundant data that's used to verify that this application data was not corrupted, or that the bit wasn't flipped. Okay, so these headers I'm showing here are the headers that I'm showing here. Although we're using UDP, I'm talking about UDP instead of TCP, so those go here, right before the application protocol. All right, so I mentioned that there's a checksum included here. A checksum is just a simple way to detect data corruption. And so you can think of it kind of like a hash. So for big files and other pieces of data, often hashes are used to check, to verify that their data hasn't changed, hasn't been corrupted. You compute the hash at first. Initially, you store that value, and then later on, if you compute the hash again, you would hope that the value is the same. Otherwise, that means that the data has changed, likely. Checksum is a simpler way to do that. That's more efficient but less secure in a sense, not cryptographically secure. So all you do is you take your data, your zeros and ones, and break them into 16-bit integers, add them all up, and that gives you another 16-bit integer. In the process of addition, so here I'm taking two 16-bit numbers and adding them up. The result here has a carry. All you do is take that and wrap it around to the lowest, least significant figure. Add that in. Eventually, you get a chunk. You get a sum. Technically, you invert the result at the end. I think that just makes it easier to check. There's no good reason for doing that. It was just an efficiency thing in the circuitry. And that's the checksum. So these 16 bits at the bottom would be included along with this original message so that the receiver could check for the consistency between the data and the checksum to make sure that no bits have changed. So to give an example of why that works, let's look at a simple message that we might want to send. So the sender wants to send the data, hello there, here's my message in purple here. Assume this is like ASCII encoded data. So every character is 1 byte, 8 bits. We have a UDP library in the sender that wants to send this message. Before it can send this message, it has to compute a checksum because that has to be included in the UDP header. Okay. To do that, it breaks it into 16-bit integers, and those would be 2 letters at a time. So you take the bit sequence of the ASCII character capital H and lowercase e, put those together to form an integer. You do that for all the pairs of letters until you get to the end. When you add all those bits together, you get some kind of binary result, which I've shown in hexadecimal. There's a carry out here, which is the B. That is shifted around to the lowest place. You add that back in, and you get the final value. And you flip the bits, which is hard to do in hex, so I've shown it here by converting back to binary and doing the flip and then getting the result. Okay, so this 1010001 is the checksum for this that corresponds to this original data. So anytime anyone looks at this message that I want to send, they can run this simple procedure to compute the same checksum, and they should get the same result. Right? It's a very simple deterministic procedure. Now the receiver gets your message. Your message includes a checksum, and that's lucky because during the transmission, it just so happens that one of these letters was changed. So let's say a bit or a couple bits, I'm not sure exactly how many bits have to change to go from an E to an A in ASCII. But anyway, the message now is, hello there, here's my massage, right? So it's a different letter here. Some bits were changed. The receiver also got the checksum that was previously calculated, which is this A3, okay? The receiver takes the message. Before it passes it to the application to use this message, it will compute a checksum and compare it to the checksum it received. It does that calculation and it finds actually that the checksum is not A3 that it received. That means that the message was corrupted. At that time, the receiver will just drop the packet. Okay. In this case, when I say the receiver, this is like an OS library for handling UDP. So from the sender and receiver's perspective, from the sender and receiver application's perspective, this bit corruption and checksum failure that caused the packet to be dropped is kind of similar to the packet being dropped in the middle of the transmission by, let's say, a router that has a queue that's full. It doesn't really matter. Internet packet transmission is unreliable. UDP packets are also unreliable. Okay, either due to a checksum failure or because a queue was full, or really a number of reasons. So checksums don't repair errors in transmission, but they do let us very easily detect errors when the data is corrupted, and therefore drop the packets, and therefore avoid cases when the applications are like receiving garbage data that they shouldn't. Okay, those are checksums. So that we were just talking about UDP. Little joke for you here. I tell you a UDP joke, but I'm not sure you'd get it. I hope by now you get the punchline to that, right? Because UDP is unreliable. It doesn't have any mechanism for acknowledgments or retransmissions. It simply gives applications direct access to internet packets so they can send a packet on the internet. Just adds a port number and a checksum. Very little additional. I mean, those are important features, of course, because it allows more than one connection to exist on a machine, and it allows bit level errors to be noticed, but it's really very simple. A very simple addition to the IP layer that comes below it. Now the rest of the lecture, really 2 lectures, are going to be about, or even is it 3 lectures? I don't know. It's a long time. We're going to spend a long time talking about TCP, which is an alternative to UDP that provides a lot more features. Okay. Just like UDP, TCP is a protocol that's usually implemented by an operating system library. And what it provides is ordering, acknowledgement, and pacing. So ordering is, because data has to be chunked or packetized, we want applications to be able to send big messages. They have to be broken into pieces. That breaking into pieces and reassembling into a big chunk at the receiver is handled by TCP. That means the ordering has to be kept consistent of the data. Remember that 2 packets sent from the same machine going to the same place can take different amounts of time to arrive, depending on a variety of things. They can go through different paths, whatever. So it could be that the second packet arrives first. We also get acknowledgement of delivery with TCP, and this allows us to get something kind of like reliability. Not exactly, because basically what this does is when there's data to send, TCP will, the sender with TCP will keep a copy of the data until it gets an acknowledgement from the sender that it received that data. If it doesn't get an acknowledgement, it'll retransmit that piece of the data. So by doing this, the receiver should be able to get everything that was sent, even though the connection is unreliable, even though the internet is unreliable. Now, TCP cannot really provide reliability in an absolute sense, because sometimes the internet is just going to be so screwed up that you can't get the data through. But at least at that point, at least the receiver and sender will know that there was a failure. The connection will fail. So either you'll get all the data in the right order and without errors, or the connection will fail. That's basically what TCP provides. TCP also provides pacing, so that the sender sends at a speed that doesn't overwhelm the network or doesn't overwhelm the receiver. This avoids filling up queues both in the routers and in the receiver, which is wasteful because you end up dropping packets. I'm going to come back to this later on, so keep this at the back of your mind, but we're not going to focus on this until later, this pacing. For this lecture, we're going to talk mainly about ordering and acknowledgement, which is the most, I think, obvious and important features that TCP provides. Okay, so this one layer of Internet protocol actually deals with many of the underlying Internet problems. We said that transmission is unreliable on the Internet in the sense that packets can be dropped. They also can be corrupted as they're moving. So the acknowledgements that TCP provides help us to deal with packet loss. There are checksums built in, just like I showed with UDP, that also exists in TCP. That helps us to detect corruption and to ignore that data when it is corrupted. We deal with the finite message sizes with sequence numbers. We'll see that later, basically by breaking messages into pieces and giving numbers to the subsequent pieces. The fact that the delivery order can be changed is solved by having sequence numbers that tell us what the order should be of the packets that comprise the message. And finally, the fact that the network links have finite speed and that queue sizes and routers are limited. Flow and congestion control will help us solve those problems, which we'll see later on. So you don't just blast data at the maximum speed. If you did that, then probably you would always end up with packets being lost, because somewhere along the way there would be a bottleneck that was slower than your first hop. But TCP provides a way to discover exactly what the best rate is to send packets, so that no one in the path is overwhelmed. Okay. All right, so to motivate this, I want you to actually stop and think. I should have a little icon here. Stop and think about how people deal with message loss on the telephone. Okay, the telephone is an earlier communication system, and people use it to talk to each other. But telephone connections are not always reliable. Sometimes there's noise in the room. Sometimes there's noise on the line. Sometimes the phone just flakes out. whatever. There's a lot of reasons why on the phone you might not hear something that someone says. And let's think about that as message loss, kind of analogous to the internet data being dropped or something. So on the phone, how do you deal with message loss? Stop and think about that for a second. All right, so I can tell you that I have two different ways. So the first one is positive acknowledgement. We call these ACKs in networking. Okay, positive acknowledgements. This is when the listener says okay or or something after each sentence, or after every so often the listener tells the talker that they have received everything okay, they understand what's happening. Okay, the purpose of this is so the sender, the speaker, if they don't hear anything for a long time, they would know there's a problem, and they might repeat themselves or ask, are you still there? So this is kind of what happens to me when I talk on the phone with my dad. Okay, he's a big talker, unlike me. And so when I call him up, he just talks and talks and talks. And I'm just sitting there saying, okay, yeah, Maybe some of you have had that experience. If I didn't say that, if I didn't say, okay, yeah, then he might not know that I was still there and listening, right? So that's a positive acknowledgement. And we end up using positive acknowledgements actually in TCP. But that's not the only way. There's another way to do acknowledgements, which is negative acknowledgement. So this is when the listener somehow notices there's a problem and says, what? Or can you repeat that? So for example, the listener might hear a message that just doesn't make any sense or has a blank in the message, and they think, oh, I must have missed something, and so they ask what was missing. So if everything is going smoothly, then under this second scheme, there's no need for the listener to say anything. If we require the listener to give a negative acknowledgement when there's a problem, then they don't say anything when there isn't a problem, and when they do give one of these negative acknowledgements, like saying what or can you repeat that, then the talker will retransmit the message in response. So the first scheme involves more interactivity, more data being sent back from the receiver, but it's somehow it's actually a little bit more reliable and dependable. The second scheme is a little bit lazier, but it's more efficient, but it's also prone to failure because you could have a situation where, let's say the talker never really knows that the receiver is getting the messages that they're sending until the receiver tells them, and it could be that they have a problem that's preventing them from communicating that negative acknowledgement back. And it also requires the receiver to have some expectation about what is being sent to them. With English language conversation or any language conversation, it's easy for the receiver to know that the conversation is going smoothly or that it has a problem. For data communication, it's more difficult. All right, so those are human solutions to message loss: positive acknowledgement, negative acknowledgement generally. What happens if acknowledgements are lost in both of these cases? You can stop and think about that. Although I kind of answered that, but let's see if you understand that. In the case of positive acknowledgements, if an acknowledgement is lost, in other words, the receiver says okay or but that okay is lost before it reaches the receiver, the talker will might retry because they think that the message wasn't received. But if those acknowledgements keep getting dropped, then eventually you'll have to give up because it has no idea that the receiver is getting the messages. In the case of negative acknowledgements, if one of these what or can you repeat that messages is lost before it goes back to the talker, then the talker will just keep going because he thinks everything's going fine, but the listener will never be able to recover from these missed messages, and the listener will give up. So in both cases, and we can't possibly build a protocol that deals with persistent message loss in one of the directions, or in either directions if that loss is consistent and never stops. But whether or not the listener or the talker or the sender or the receiver gives up depends on what kind of acknowledgement you're using. Okay. But like I said before, in this on the internet, we tend to use positive acknowledgements mostly. Okay. So let's see how we can build a simple, reliable transport protocol using a very basic form of acknowledgements. I'm calling these naive acknowledgements. In practice, we're going to do something more complicated because we'll see there's a little bit of a problem with this. But let's just see how this operates so we understand. So I'm showing a diagram here where the time is flowing downward, and we have a sender and receiver, and these lines show packets being transferred, messages being transferred, and the messages are at an angle because it takes some time for a packet to flow over the internet to the receiver. Okay, so the sender sends the packet 0 at this time here. Eventually, it gets to the receiver. When the receiver gets that data, great. It sends an acknowledgement back, and that acknowledgement has is the acknowledgement to packet 0, so we label it acknowledgement 0. It sends back, so this receiver says, okay, sender, I got your message 0. That's what this acknowledgement says. And once the sender gets that message, it can move on to send the next packet, right? It knows that the first one was received, it can move to the next one, and so on and so forth, right? Very simple. This is the scenario with no loss, and this works, right? It's very simple to implement, too. If there's a packet loss, it also works, but the behavior is a little more complex to deal with the loss. So let's say the first packet was received fine, packet 0. The second packet, which is labeled packet 1, is lost when it's on the way to the receiver, right? Shortly after it's sent, it gets lost. Now, the receiver never gets it, of course, so it never sends an acknowledgement. Now, the important thing is that who reacts to fix this problem? Well, the receiver can't do anything because the receiver has no idea anything was sent in the first place. The sender, however, knows that it sent a message, and eventually it knows that if it doesn't get an acknowledgement, there was a problem, right? So that eventually is a timeout. So the sender waits for a certain amount of time, called a timeout, and this is like the maximum possible round-trip time it expects between itself and the receiver. If after, I don't know, let's say 10 seconds, just to make it really easy, if after 10 seconds I don't get a response back over the internet, I'm pretty sure that packet was lost. So what the sender does at this point is it resends that very same message, and then the receiver gets it this time and sends back an acknowledgement. Of course, if the system is so messed up that every packet it sends is lost, then of course you're never going to be able to proceed. We're assuming the internet is unreliable, but that only a small fraction of messages are lost, and that eventually, if you keep retrying, eventually the message will get through. Okay, and that's how the protocols on the internet are designed to deal with temporary packet losses. Okay, there also can be a packet loss that occurs in the other direction, and the response is a little bit different, but basically it's the same. So first message gets through, the acknowledgement comes back. Second packet, this time the second packet is received, and the receiver, of course, sends an acknowledgement, but this time the acknowledgement is lost, not the original packet. Now, think about this from the sender's perspective. Now, the sender has no idea what's happening in this right-hand side of the diagram. The sender only knows what it sent and what it received. Okay, the sender cannot observe the whole network. The sender cannot observe the receiver. The only thing it knows is through messaging. It is through the message. It knows the messages that it receives and what it has sent. Okay. It sent this first packet and it never gets a response. Of course, it doesn't know whether the response wasn't received because its own message was dropped or the acknowledgement was dropped. But anyway, eventually after 10 seconds, just like before, the sender times out and retries. Okay. The difference here is that the receiver, when the receiver gets this first packet, it's a little bit weird because it already got this packet before. So, how does it know it's the same packet? Because it has the same number attached to it. These are called sequence numbers, like I said before. It knows that it's not new data. It's not a third piece of data. It doesn't add this data to the previous data in sequence because it has the same sequence number, 1. So it knows this is a duplicate. Now, if you're not careful in designing this, you might just say, okay, I don't need to do anything because I already got this data. I already acknowledged it, right? Why would I need to do anything else? But it's important, actually, that the receiver send it another acknowledgement, even though it already sent this acknowledgement before, because of the possibility that, maybe it was the acknowledgement that was lost, and that's why I'm getting this packet again. Okay, and in fact, that's what happened. Right? So in general, if the receiver gets a packet twice in a row, the same packet, that means that the original acknowledgement that was sent was lost. So it needs to send that again. If it doesn't send that, then the sender will not be able to make progress and send the third packet. Okay? Great. Final variation, which you may not be obvious, is called a premature timeout or delayed acknowledgement. Okay, I said before that the timeout, we after a certain amount of time, we know that the packet was lost. And I said 10 seconds. I gave this like absurdly high number. 10 seconds is way bigger than a round trip time you'll ever see on the internet. So it's a safe number. But it's foolish to choose a timeout so high because it causes bad performance, right? We expect we expect packet loss to happen. We don't want our applications to be slowed down by 10 seconds every time there's a packet loss. If we could somehow choose a better timeout that was like a little bit closer to the maximum, right? So we have to set this timeout pretty carefully because there's a trade-off, right? Setting a timeout too long will mean that our application is slowed down more than it needs to be. Setting it too low, though, means that we might time out even though there's an acknowledgement coming back because we waited for a while, but we didn't wait quite long enough to get the acknowledgement. And actually, because there's a trade-off here and we have to set this timeout experimentally, we'll see how in later lectures, there is the possibility that there was no packet loss, yet there was still a timeout. So the second packet was sent up here, the receiver got it, it sent back an acknowledgement, but for some reason this acknowledgement was a little bit slow coming back compared to the previous acknowledgements, or alternatively, the sender just set a shorter timeout than they should have. Okay? We'll see why later on this timeout is not... Setting the timeout value is a little bit tricky, and you can't always set this absolutely correctly. There's always going to be some variation in the delivery time of packets. Okay, so this acknowledgement is on its way, but the timeout expired. So the sender actually resends the same data, like in the previous scenario. The receiver gets a duplicate copy of the same packet, like in the previous scenario, and it does the same thing. It knows it got this data, but it doesn't know. It suspects that maybe its acknowledgement was lost, so it resends the acknowledgement. Now, in fact, its acknowledgement was not lost, but it was kind of delayed. But it doesn't matter. It does the same thing. While that's happening, though, notice that the first acknowledgement does come through. And now at that point, the sender can say, well, an acknowledgement came in, so I'll move on. Actually, the sender doesn't really know if that acknowledgement was from the first copy or the second copy of that packet. It could have been like a really quick back and forth that caused that acknowledgement, but it doesn't matter. All it knows is that the sender did tell it that it received the second packet, so it can move on to the third packet, and it does that. Okay. And later on, it gets a duplicate acknowledgement. This acknowledgement of the second packet 1 comes in a second time, and but that's okay. At that point, it doesn't have to do anything because it already has sent packet 2. The fact that it was acknowledging packet 1 doesn't matter. Okay. All right, so that's reasonably simple approach to having reliable transport on the internet, even though packets can be lost. It's easy to see that this is correct in the sense that packets are delivered in the right order, and that we can cope with temporary packet drops or network failures, let's say. We never send packet n until we get an acknowledgement for packet n-1. That ensures that the delivery is in the right order. This timeout was necessary to decide when a packet is lost because the sender can't really know the status of a packet until it gets an acknowledgement. So this is kind of like a hack in a way, but it's the best we can do. We saw that if a timeout was premature, then the sender may retransmit a message unnecessarily, but that's okay because both the sender and receiver can discard duplicate or redundant packets. And there were some rules here about when you need to retransmit an acknowledgement and a packet, which are pretty simple, right? Pretty intuitive. Notice that at most twice the necessary packets will be in flight in transmission. So it could be that you have your original packet that's in flight, and then let's say an acknowledgement is late, so you send another copy, but you're never going to send a third one because you only have one timeout. The timeout is based on when the first copy of the latest packet was sent. All right, but let's look at the performance here. It turns out the performance is not so great here. The problem is essentially this is what's called a stop and wait protocol. So we send a message and we stop and we wait for an acknowledgement. And this means that the round trip time of the network, the time it takes for the packet to get there and for the acknowledgement to come back, dominates performance. And round trip time can be fast or slow. Theoretically, the round trip time, the latency of the network should be independent of the throughput. We'll see here that with the stop and wait, the latency limits the throughput of the connection. We don't want that. And we'll have a way to fix that. Okay, but let's look at an example here. This is assuming an ISP has a fiber optic link, let's just say from New Jersey, which is an important hub of the telecommunications industry, from New Jersey to San Jose, California. This is a really pretty fast link, 1 gigabits per second. Propagation time is determined by the speed of light at around 15 milliseconds. And the packets we're sending are limited in size because that's the way the internet works, and they're about 1.5 kilobytes. All right. So those three numbers will actually limit our throughput, determine our maximum throughput if we're using a stop and wait protocol. Because what we'll do is we'll send a packet. Packet needs to get there. A response needs to come back. Then I'll send the next one. And that pattern will determine the rate at which I send data. Okay. The round trip time for packets is the propagation delay. Technically, there also is a little bit of delay that's introduced by transmission. So I have to take that 1.5 kilobyte packet, those 1,500 bytes, and send them 1 bit at a time at a rate of 1 gigabit per second. So the math for that means that packet is sent in 0.01 milliseconds, and the 30 milliseconds comes from the propagation delay there and back. Okay, this is really dominated by the round trip time as opposed to the packet transmission time. Now that means we're sending 1.5 kilobytes of data every 30 milliseconds. If you just divide the two and adjust for the units of bit to byte, you'll see this gives us only a throughput of 250 kilobits per second, which is like 5 times a 90s dial-up connection. Really slow. Really, really slow. Okay? This is like 2G or 3G mobile speed. It's not what we want. So when we added acknowledgements, we added stop and wait, we ended up with 4,000 times slower performance than without it. Because remember, that I'm comparing this 250 kilobits per second with the peak bit rate is actually 1 gigabit per second of this link. So bits can flow, 1 billion bits can flow per second on this link, but I'm only sending 250,000 bits per second because I send a burst of bits and I wait for a long time for those bits to flow to the other side and comes back. Okay, so this is illustrated in this diagram, which again has time flowing downward and the sender and receiver, and then we have an angled path for data because the data has propagation delay, right? So the sender starts sending the first packet at time 0. There's some time period, so the height of this blue segment is the time it takes to send one packet. So you're sending bits at a rate of 1 gigabit per second. You eventually get through the 1,500 bits. That time it takes is the length of the packet divided by the bit rate, L over R. But then you stop sending because you're waiting for an acknowledgement. And in the meantime, the data travels over the link. It gets to the receiver. So the difference in height between t equals 0 and when the first packet arrives, that's the 15 milliseconds that we calculated, that we were given for the propagation delay. So this here is 15 milliseconds. First packet arrives at the receiver. Let's say the receiver has to get all the bits in the packet. So eventually, after this short time period, the receiver has received the whole packet. It can start processing it. And let's say it sends an acknowledgement immediately. The acknowledgement, again, has to travel 15 milliseconds worth of distance before it's received. And at that point, the sender can say, okay, that packet was received. It's acknowledged. Let me move on and send the second packet. Okay. So all this white space in this diagram is wasted time. It's when the link is not being used. Okay. This is idle time. So this white space represents the inefficiency. And for the last example, this is not to scale. Like the blue part would be really thin and the white would be really huge because we have a really high bit rate connection going over a really long distance. Okay. And this diagram kind of shows that. Right? New Jersey to California. The solution to this is called pipelining, where we don't just send one packet and stop and wait for the response. This diagram shows one packet being sent and only one packet over this long link. Instead, what we want to do is send one packet, but then after that send another and another and another and another. Even though the first one was not acknowledged yet, we move on and send the next packet. If there's more data to send, if we're like downloading a big file or streaming a movie or whatever, we know there's more data that's going to have to eventually be sent. Okay, sure, the previous packet wasn't acknowledged yet, but very likely it will be. So let's just assume that eventually it will be acknowledged. That it will be acknowledged, and we'll move on to the next one. Okay, we'll put lots of data in the pipe. Don't have idle space in the pipe, and the acknowledgements also will come back in parallel. So when the receiver gets the first packet, it'll send an acknowledgement. When it gets the second packet, it'll send another acknowledgement, and those acknowledgements also there'll be many of them in flight at once, filling this pipe on the way backward. Okay. We have many packets in flight. It's kind of like parallelizing the stop and wait protocol. You're parallelizing transmission and acknowledgement. But this introduces a lot of complications, which we'll see. Okay. We need buffering in this case, and we need a more complex form of acknowledgement. When I say buffering, I mean that the sender needs to keep copies of, in this second scenario where there's a lot of data in flight, that means that the sender needs to keep copies of all of that data because any one of these packets might be lost, so any one of them might have to be retransmitted. Similarly, the sender has to have some way to know which of these were acknowledged and which were not. The receiver also might need a buffer to store lots of different packets from different positions in the stream because they might arrive out of order. And yes, it's a lot more complicated. Later on, we'll also see how flow and congestion control prevent this pipe from being overwhelmed so that we send this data at exactly the right rate so that packets are ideally or not lost because packet loss is inefficient. And we'll see why that is later as well. So buffer, by the way, is just a term for a queue of data waiting to be consumed in the way we're using it here. Buffering and queuing are kind of the same thing. All right, so going back to the same diagram with link, where we're showing link utilization. When we add pipelining, we get more blue. We get more utilization and less idleness. We don't get 100% utilization, though. But we have a certain number of packets we're going to send in parallel. In this case, we send 3 packets, and then we stop and wait. So there's still a little bit of stop and waiting, but we're not stopping and waiting after each packet. We send a bunch of packets, 3, and then we wait. So the first packet arrives, it sends an acknowledgement, the second one, another acknowledgement, third one, another acknowledgement. And then when the sender gets an acknowledgement, then it can move on. So the idea here is that the sender has a window with a finite size. The window size is the maximum number of in-flight packets that it's going to allow. Okay, it's 3 in this example. We'll see also in TCP that the window size is not... In practice, it's not counted by the number of packets, but the amount of bytes. Not a big difference. For now, we're going to talk about windows in terms of the number of packets. We're going to assume all the packets are like full size, let's say. Anyway, so why is this? Why are we limiting ourselves in this way? Seems like we're introducing inefficiency where we don't need it. Like all this wait time is inefficient. Well, the reason we have a finite window size is because all these packets that are in flight need to be stored by the sender. Because they might, any one of them might be lost, so any one of them might have to be retransmitted, Okay, so the sender may not have enough space to store a ton of data that's in flight. That's one reason. The receiver might not have enough space to store a ton of packets that are received but out of order that it has to reassemble. That's another reason. But in practice, those are not that critical because, I mean, computers have a lot of memory. So you actually can store quite a lot of data that might need to be retransmitted. The real reason won't become obvious really until the next lecture, or is it the one after? Anyway, when we talk about congestion control. So this window size, it turns out, is actually a variable that we use to control how much load we're putting on the network. If we make this window size unlimited and we just keep sending data whenever we can, it very well could be that we overwhelm the network and we end up losing packets. So this is a variable we'll control to limit the average load we put in the network to pace the connection at the right rate. So the window size is a mechanism for pacing the connection. For this lecture, though, we're going to just assume it's a constant that's given to us. Okay, and let's just assume naively that the reason is, the sending machine has limited memory. Let's just keep it simple and go with that for now. But like I said, in reality, it's a way of controlling the pace of the network, of the connection, for the benefit of the network, really. Okay. So when we parallelize acknowledged data transfer, we need to introduce sequence numbers. Sequence numbers just identify the packets. We saw that we actually even had sequence numbers in the stop and wait example, though we didn't really need them except to distinguish different acknowledgments from being new acknowledgments versus old acknowledgments. So we kind of needed them, but only a little bit. We just talked about pipelining reliable transport. This is a way of parallelizing the transfer of acknowledged data. When we introduce this parallelism, we introduce the possibility for out-of-order delivery. We have to handle that. The sequence numbers are a way of dealing with that. So every packet has a number, and the receiver then becomes aware when there's a gap in the data that they need to wait for a late packet. Excuse me. Acknowledgements also carry sequence numbers, as we saw in the example, the first example, so that the sender knows which of the many packets it has recently sent is currently being acknowledged. Okay, because it's possible that 3 of them were acknowledged, but one of them was not. So that one packet was lost. That one packet needs to be retransmitted. Okay, so that was the basic idea of pipelining. But to actually implement it, there are a couple of different ways. So I'm going to the remainder of this lecture and next lecture is going to go over some details of how to implement pipelining to and ways of dealing with the trade-offs inherent in pipelining and the different designs for pipelining. Okay. The first way of designing pipelined, so in other words, high performance acknowledged data transfer, so reliable transport, is called go back N. This is the simplest way of doing it that I'm going to present to you. And it works fine. We'll see later on it has a few shortcomings, but it's pretty simple. Okay, so go back N is a scheme that uses a window size of N. The sender can have up to N packets in flight. That's the definition of a window, right? And what makes go back N simple is that the receiver sends cumulative acknowledgements and only cumulative acknowledgements. So instead of having instead of telling the sender, I got this particular packet or I got that particular packet, I got packet 4, I got packet 3, what the receiver always does is it says a cumulative acknowledgement that says I got everything up to a certain sequence number X. Okay, so the receiver is constantly telling the sender what the last position in the byte stream it has gotten everything up to. Oh, excuse me. So, and if the sender keeps a timer for the earliest unacknowledged packet that it has sent, and after some timeout interval, it sends all the packets that it has available that it has previously sent that has data for after the last acknowledged packet. Okay. Now, this So I realize right now this is a little bit probably is a little bit confusing. This diagram, and I have some animations. I have a couple diagrams and an animation to try to clarify this. This diagram on the bottom shows a stream of data. So the left is the earliest data, the right is the later data. This is from the sender's perspective. So the sender, like in your project, the sender might be calling a socket send function that passes in an arbitrary amount of data. The underlying OS library will break it into segments or packets, and those are the different blocks shown here. The green ones are the ones that have been sent and acknowledged. The yellow ones are the ones that have been sent but not acknowledged yet. So both green and yellow packets have been sent. The green ones have already been acknowledged. The yellow ones are in flight, or the acknowledgements are in flight. And then these blue ones, these blue spaces here, are positions in the stream where the TCP library has not yet received data from the application, but once it does, it will be ready to send data because this position does not extend past the window size. The window size is the maximum amount of data that is unacknowledged and can be in flight. Maximum amount of unacknowledged data that can be in flight. Okay. So when an acknowledgement comes into the sender, the window will be moved. Whatever packet number that is that was acknowledged will become will become green, basically, and everything to the left of it will become green. And the sender can forget about that data. This green data no longer has to be stored on the sender because it's already been acknowledged as received. This yellow data has not been acknowledged. It's been sent, but it has not been acknowledged, so the sender needs to keep a copy of it just in case it does not get acknowledged and has to retransmit it. If a timeout expires, all of these yellow unacknowledged packets will be retransmitted. And whenever an acknowledgement comes in, if that acknowledgement is different than the last acknowledged packet, in other words, if the acknowledgement is let's say this third yellow packet, then three of these yellow packets will become green. We will have gotten new information about data that was received. The window will slide over, and a new timer will be set. Okay. As long as acknowledgements are coming in and those acknowledgements are increasing in number, then there's no reason to ever retransmit. That indicates everything is going well. Packets are being received. The receiver's telling me that it's getting new data. The only time when there's a problem is when the no acknowledgements come in, or acknowledgements come in with the same number. Where the receiver is saying, I'm not making progress past this point. And at that point, that you would need to retransmit. Okay. Okay, again, like I said before, we'll have a couple of ways of seeing this in action to clarify how this works. So here's a scenario where, as a simple example, the window size is set to 4. So this blue block, I guess, indicates the packets that can be sent. This example assumes that the application has provided an unlimited amount of data that's ready to go. So the application has a ton of data it wants to send, and now it's up to this transport protocol to send that data using the finite window that it has. Okay, so the sender will, like I said, it has a ton of data to send. Window size is 4, so it'll send 4 packets, right? 0, 1, 2, 3. Once the 4th packet is sent, it'll stop because the window is full. There are 4 unacknowledged packets, which I had colored yellow in the previous slide. Okay. When packets are received, the receiver will send an acknowledgement which indicates the highest packet number that it has received all the data up to. So it'll send a cumulative acknowledgement. So in this first case, it sends acknowledged 0, saying I received everything up to and including packet 0. The second case, it sends acknowledged 1, meaning I received everything up to packet 1. This third packet is lost. Okay, so when this 4th packet arrives, the receiver, it doesn't acknowledge 3 because this scheme uses cumulative acknowledgement. So if it acknowledged 3, that would be telling the sender that it has received everything up to and including 3. In fact, it has not. It has not received this packet 2. So it sends acknowledge 1, which is a duplicate of the previous acknowledgement, because again, it has received everything up to and including only packet 1. So it tells the sender that, and it throws away packet 3 because it has not yet received packet 1. It doesn't have a place to put that. It doesn't. It could. We'll see later on that what you would want to do if you were more clever is you would save this to reuse it later. But what the simplest possible protocol does is throws out that packet. Okay. If we go back to the sender, those first 2 acknowledgements that were sent are eventually received. When that happens, the window slides over. Packet 0 can be forgotten forever because it has been acknowledged. The sender has gotten an acknowledgement for it. Same thing for packet 1. That can be forgotten when it gets a cumulative acknowledgement for packet 1. The window slides. When the window slides, there now is another packet that is that can be sent, and so the sender sends packet 4 and packet 5. Now, again, when those packets are received, the receiver can't do anything with those because they're out of order. It has still not received packet numbered 2, so it throws those out and resends acknowledgement of 1. Okay. Now, eventually a timeout expires on the sender side. That timeout is a timeout from the time when the last unacknowledged packet was sent. So the sender keeps track of when all the packets were sent, and it compares that to the current time. And if so, it's at this point shown here with the red clock. Packet 2 still has not been acknowledged, and the timeout plus the time packet 2 was sent is greater than the timeout limit constant that was defined. Okay, so at that point, the sender retransmits everything that has not yet been acknowledged. Now, specifically, everything that's not been acknowledged is all the data that's in the window. So it sends packets 2, 3, 4, and 5 all over again. Now, this time, assuming there's no loss, eventually, then the receiver, if everything goes well, will be happy. It'll start acknowledging the packets in order, right? Because finally, down here, it gets a new piece of data it can use, which is packet 2, after all this time, and it sends acknowledgement for 2, and so on. And then the receiver will move its window and proceed based on that. Okay. So I'm going to show a little demo of this, and you can do this at home, and I encourage you to do so. So here is a little applet which was provided by the book authors, and it shows the go back end protocol in action. I'm going to make this a little bigger. Okay. So, a little bigger. Okay. On the top, we have the sender's window and the sender's data stream. And on the bottom, we have the receiver's window and the receiver's data stream. So the receiver has a window of just one. The receiver doesn't really have a window per se. Whenever it gets data, it only is willing to accept one packet of data, one sequence number at any given time. That's one of the simplifying features of this protocol. So what I can do with this applet is send packets like so, and I can kill packets. So when things go well, the receiver gets the packet it expects, which is the next one, and it sends an acknowledgement. Whenever an acknowledgement comes in, then the receiver moves its window. Now, in the previous example, I assumed data was already ready to go. In this case, there's a button to provide more data, so I have to actually tell it to send more data. Now, at this point, notice that I can try to send more data, and I'm clicking. You can probably hear that, but the program won't let me send more data because there's already 5 packets in flight, which is the window size. Okay, let me reset this. So if now this time I'm going to be more evil, and I'm going to kill a packet. So if I send 3 packets and I select one, I can kill that one. Okay, so this second packet was never received. Notice that the receiver was really waiting for that particular packet. When the third one arrived, it ignored that packet. Okay? And the only thing it did was send an acknowledgement for packet 0. So at this point, the receiver has 2 packets that are in flight that were sent but unacknowledged. It's not even, eventually the timeout expires, as it just did, and it says, okay, I'm never going to get an acknowledgement, so let me just send again. That's what it did, and this time the packets are not lost and they come through. So now let's see what happens when an acknowledgement is lost. I'm going to send 2 packets again. I'm going to cause the first one's acknowledgement to be killed. Okay, so this packet 3, acknowledge 3 was lost. Here's a cool thing. Watch that. There was no problem there. The acknowledgement for packet 3 was lost, but the acknowledgement for packet 4, the next acknowledgement, did come through. And because acknowledgements are cumulative in this particular protocol, the receivers can actually make use of that acknowledged 4 to imply that 3 was also received. Because the sender would never have sent acknowledged 4 if packet 3 had not already been received. So the sender thinks either the acknowledgement for 3 was delayed maybe, or it was lost, but it doesn't care. Okay? So this is something you can use, and you can try different variations of packet loss and see how they work. I encourage you to do that. So look now. See how these all are acknowledging number 6? That's because when the last 2 came in, packet 7 was lost, so it acknowledges the earlier one. The earliest contiguous segment, that it always acknowledges the packet that is highest in the continuous stream of data that was received. Okay, so that's that. Pretty cool. Nice demo. Demonstrates it. Okay. So the advantages of this scheme are that it's pretty easy to implement. The logic is pretty easy. When you play through the demo, the logic becomes pretty easy to see. The sender just stores the number of the last acknowledged packet, and it maintains a timer. When a timer expires, it resends everything in the window. Pretty simple rules. The receiver stores the expected sequence number. That it has a window which is waiting for one particular packet, and whenever a packet arrives, if it's the one it expects, great, it increments the expected number to expect the next one. If not, then it just sends acknowledgement for whatever the current expected is -1. Okay, and the packets can be passed immediately to the listening app because they're always accepted in the right order. The shortcomings here are that it's kind of catastrophic when a single packet is lost or delayed, because all the in-flight data is lost. Like, the receiver doesn't save early data, and the acknowledgements are so it's kind of a coarse-grained approach. We lose an entire window of data due to one bad packet. What that means is, like, the example is, let me reset this, and so if I send a bunch of data, one packet loss, I'm going to kill one packet, just the first one. Even though I only killed one packet, all that other data transfer was useless, and it'll have to be redone. So when a timer expires, I'm going to have to retransmit everything, not just that one packet. Yeah. Now, the second approach to pipelining we're going to look at is called selective repeat, and it overcomes those shortcomings in terms of it reduces the impact of a single packet loss, but it's a lot more complicated. It requires a sender to keep many timers, one for each in-flight packet, and for the acknowledgements no longer are cumulative, but the acknowledgements are given for individual packets. That means that a lost acknowledgement actually has a little bit more impact, but that's a slight trade-off there. Okay. So in this case, the window size n, we still have a window, but that definition is a little bit different. It limits the maximum range of unacknowledged packets, not the number of unacknowledged packets. The receiver drops received packets when sequence numbers are outside the window, but the receiver does actually save packets that are early, meaning that it receives packet 3, but packet 2 was not received, for example. It will keep that early packet and try to use it later. It'll wait for the gap to be filled. Once the gap is filled in, it can actually provide the full chunk of data to the application. We do still have this window. Now that we're accepting packets with arbitrary sequence numbers, we have to be a little bit careful. We still only allow a limited window of sequence numbers to provide data, because there could be an old connection on the same packet that happens to have a packet arrive late or something. We don't want packets from old connections to influence this connection. We'll see later on how randomized sequence numbers fix that problem, but that's like next lecture. All right, so we're acknowledging packets individually, and we are retransmitting only individual packets. But it becomes more complicated because we now have kind of like, within this window, we have some packets that were acknowledged, the green ones, and we also have some that were unacknowledged, the yellow ones. So there's like, these can alternate in state, not just all be unacknowledged. The receiver also now has to have a window, not just a single slot for accepting packets. So the receiver will accept packets that are like later on in the stream if they come in early, even though it has not received earlier packets, and it'll save those. Okay. And the sender window advances whenever it has filled in the gap, and eventually the beginning of this sender window is the end of the data that can be forgotten, which is the continuous stream of data that has all been acknowledged. This window has to include the earliest unacknowledged packet, basically, in other words. And on the receiver side, once you have new data that to the left of this window, you send it to the application and you slide your window forward. So this gray slot is waiting for data. This yellow, magenta or red colored packet is one that was already received. We cannot give this red data to the application yet because the application is expecting data to come in order. It's received this white data, but it has not yet received this first gray packet. We can't provide this gray packet yet because it's still in flight. Okay, well, once it does come in, though, we can give three packets worth of data to the application. All right, so there's a demo page for this as well. And we'll see now a little bit of a different behavior and less inefficiency. So when we send a bunch of packets, if I kill the second one, notice that the third and fourth one are they're received and they're acknowledged individually. So the receiver keeps a copy of these early packets, we call them. It doesn't have the second packet, but it has the third and fourth. The sender also got an acknowledgement. So the sender knows that only one packet was is unacknowledged so far. It knows that these other higher ones were acknowledged. So when a timer expires, as it just did, it can retransmit just one packet. And when it comes in, watch this. 3 of the packets can be delivered to the application in response to just one packet coming in, because it fills in a gap where there was higher data that was like stored, buffered, waiting to be delivered. Okay. We also can play with acknowledgements being lost. It's kind of the same thing. If an acknowledgement, let's say this packet 5 is the acknowledgement is lost, it doesn't affect the higher numbered packets. So the receiver actually has everything, but the sender is not sure that the receiver has packet 5. So eventually the sender will retransmit that one. Even though in this case we know technically it's unnecessary, but the sender can't really know that because it didn't get an acknowledgement for it. The acknowledgements that the sender got for 6 and 7 didn't really tell it anything about whether 5 was received. Okay. There still is a window that limits the amount of data transferred. So if I try to send as fast as possible, just like before, there's going to be a limit to how much I can send. Okay. And this limits the amount of memory that this receiver has to keep and that the sender has to keep. But like I said before, also it is important for keeping the network from being overwhelmed. It's called congestion control and flow control. All right, so that was a demo for that. Almost done. Just one more thing for this lesson. Notice with these sequence numbers that so I guess if you just keep using integer, if you use integer starting at 0, then that might seem great. Might seem like a fine plan, but eventually you run out of integers. In TCP, we have a 32-bit number that's dedicated to sequence numbers. Like there's a certain fixed size slot in the headers for putting the sequence number. eventually you run out of space in a 32-bit number. So 32-bit number, actually in TCP, it's used to measure bytes, not packets. So it goes up to 5 gigabytes. Once you send 5 gigabytes on a single connection, which is quite possible, if you're streaming a high-def movie off Netflix, you might get more than 4 gigabytes of data over 2 hours. Then the numbers will wrap around and get back down to 0. So the way sequence numbers work is that they wrap around. They kind of work in this modular way, and that's fine, except there can be a problem if you reuse the sequence number while the old one is still being used. So here, a very simplified example has 4 sequence numbers, and then they loop around back down to 0. So 0, 1, 2, 3, then 0 again. If your window size is 3 and you're using only 4 sequence numbers, eventually what will happen is you might have 2 packets in flight, kind of, or 2 packets that are being considered by the system with the same number but actually refer to different parts of the data. So here I sent packet 0, packet 1, packet 2. The receiver got all of them except the acknowledgement for it got all of them, and then packet 3 is sent. The 4th one, that one is lost. It moves on to the next packet, packet 0, and sends that. The receiver will accept packet 0. Sorry, this example on the left doesn't have a problem. The problem arises on the right-hand side when, in this particularly bad case, all 3 packets were lost. No, sorry, all 3 packets were received, but the acknowledgements were lost. And that means that the sender eventually will time out and retransmit packet 0. So it's retransmitting an old packet. But the receiver, since the window is too big relative to the range of sequence numbers in use, it'll think that packet 0 that's retransmitted is actually the next one. And it'll end up accepting that in repetition in the stream instead of ignoring it as a duplicate. Okay, so stop and think about that and how to fix this. And I want you to think specifically about what the problem was here and how to fix it, how to avoid sequence numbers from being confused because they're reused. I kind of mentioned this in a way, but the problem basically is that the window length is more than half the size of the sequence number range, and that allows an overlap. The problem is basically that the sender's window and the receiver's window, in the worst case, can be offset by a full window size. So like here's the sender's window, and here's the receiver's window. If there's a possibility for that to, for these to overlap because the using modular arithmetic, you're overflowing the numbers. You never want these 2 ends to meet, and that only happens if the window length is greater than half the maximum sequence number. All right, so to recap today's lesson, we talked about UDP briefly as a connectionless packet-oriented transport protocol. Basically gives applications access to send unreliable, unacknowledged packets. It gives you port numbers and checksums to allow multiple connections to exist on a machine and to allow you to detect bit errors. But it doesn't provide much else. TCP provides a lot of features to give you delivery confirmation, the correct ordering of your data stream, and we'll see also congestion control in the next lecture. But in order to implement delivery confirmation and to break a big message into little pieces and make that be delivered correctly and reliably, we started off using stop and wait, which was really inefficient, but that introduced the idea of acknowledgements. We really want to pipeline transfers to allow multiple packets to be in flight. This introduced the need to have a window size. The concept of a window size was the number of packets that were in flight. And then we showed go back N as the simplest pipelining protocol that we're going to discuss. This uses cumulative acknowledgements, which simplifies the work that both the sender and receiver have to do, but then the cost of a packet loss is greater because both sides have less information about what has happened, because they remember less, and that means they have less. They have to react in a kind of a dumber way when there's a problem. Selective repeat was more complicated. There was buffering on the receiver side, so a window of that was in the stream where data could be inserted. This would reduce unnecessary transmission. The sender had to keep more timers for all the packets that were sent, so that added some complication. But it was more efficient, like I said. So next time we're going to go into we're going to go into TCP, which actually is neither go back N nor selective repeat, but a combination of the two. And then we're going to see what flow and congestion control are, which is the final half of TCP. Okay. So, like I said, this is an important part of how the internet works. How they have this unreliable network that somehow allows us to have reliable connections for building applications that can assume. We build an application where this TCP protocol hides the fact that the internet is unreliable, which is really pretty cool. All right. See you later.